Hello GGS 300 and welcome back to what is going to be the fourth lecture for quantitative methods for spatial science, and today we're going to be focusing on spatial descriptive statistics. So well done on getting those assignments submitted. I've now marked them. I think generally people did very well. It was great to see no one kind of completely fail those submissions, and there was good work generally across the board. I tried to make sure that I would give marks if, for example, you didn't quite get the right answer, but you gave the right kind of working out, or you were kind of along the right lines. So I was kind of generous with the marking scheme. But if you've got any further queries about that, then please don't hesitate to get back to me, okay? And obviously there's going to be a lab session today, and then after that lab session there's going to be a third assignment which will be set, which will be due the following Thursday from today, okay? I did have a couple of things to say about the assignments that were submitted, so please can you paste the R code at the end of the Word document which you submit. So the kind of perfect template for me is if you say, you know, question 1, and then you put your answer to question 1, and then you go to question 2 and you put your answer, and then at the end all I'm really asking for you to do there is to just copy and paste the script that you created in your R project. Just copy and paste it at the end of the Word document so that I can just take a look at the code very easily in one place. So a couple of people kind of put the code with each question, and then it's kind of hard for me to also to kind of revert each time. So if you could just post it all at the end, that would be really useful, thanks. And I think I did have a couple of you reach out to me, and that was great because it was good for me to kind of liaise with you and understand what problems you actually had. If you do have any particular problems, you know, the standard way to solve an R problem if you've got a coding error is essentially first just to copy and paste that error, okay, into Google and just see what comes up, and then read the actual responses, for example, on Stack Overflow to those problems that people might have posted before. Because let's face it, whatever problem you're going to have, someone will definitely have faced it before. So I just want to make sure that you basically try to utilize all of the resources to you before you head out, kind of reach out to me. In step 2, then consider posting a Stack Exchange or a Stack Overflow question with a reproducible example or reprex. And then if you can't solve that issue, then reach out to me and just basically send me a screenshot of your code and the error message, and then I'll basically get back to you with some advice. I did feel a little bit like some people maybe lost some marks on the assignment because they kind of gone down one path and that path was kind of wrong. And obviously you got the wrong answers, but you're kind of quite close to getting there. And I just felt like maybe if you reached out to me just to be like, oh, Ed, is this kind of right, or am I on the right tracks? Then I could have tried to kind of shuffle you on the right path. So don't hesitate to do that in the future if you want. Okay, so don't worry about reaching out to me. I'm here to help you through. Course update. There will be midterms, as you know already, and I'll be setting those for the first third of the course relatively soon based on the descriptive statistics part. So watch out for the announcements that will come. I think that'll be in the next 2 to 3 weeks. So today, let's get on with what is going to be a focus on spatial descriptive statistics this week. So the concepts and techniques related to carrying out the kind of descriptive statistics which we carried out in the previous lecture, but this time within some sort of geographic space, okay? And it's going to require us to do some different type of math. It's going to require us to do some different types of spatial processing, and hopefully this will kind of cement your kind of basic understanding of spatial statistical processes. So within concepts of spatial descriptive statistics, what are we really talking about here? So we spoke the last time about those 3 key areas, so measures of central tendency like the mean or the median, measures of dispersion, so that's like the range is a basic measure, or more better metrics like standard deviation, coefficient of variation, or actually the measures of the shape of a distribution, so that could be the kurtosis, basically how skewed the data is, and also the kind of the shape, vertical shape, whether it's leptokurtic or platykurtic of a distribution. Okay, so as I mentioned already, spatial statistics can do something similar, but it's all within some sort of spatial context, and people might refer to this also as geostatistics. So there's a lot of different names for basically the same thing, and these aren't hugely complicated measures. Okay, so we're not talking about really complicated math here. They're usually single equations, and they're relatively easy for you to kind of produce manually, as we will do within R, for example, or just a spreadsheet. Or maybe you could just do them within a graphical user environment for spatial processing data. So, for example, within ArcGIS or QGIS. Okay, so let's just have a little bit of a comparison between those spatial and non-spatial measures. Okay, so in table 4.1, this is actually taken from the book. We have those non-spatial measures which I discussed already. So the mean, for example, the standard deviation, the coefficient of variation, and then we have relative spatial measures for them. Okay, so the mean center, the standard distance, the relative distance. We'll go through those today. So we'll use these to conduct studies explicitly on spatial data, to summarize point patterns that we might have, to kind of emphasize the degree or to quantify the degree of variability that we have within our spatial data that we might collect. And generally for it to be to actually use these types of statistical approaches, then you have to have hard coordinate data. Okay, so at least, so this is coordinate data which contains x and y points, you can have polygons and more advanced spatial features like that, but remember that under the hood of those types of shapes are basically just a set of xy coordinates anyway. So most of this work is going to focus on points, just single points in space that have an x and a y coordinate. But actually you can take those more advanced spatial features if you have them and convert them down into point data. So for example, if you've got a grid, you can just take the centroid of the grid square for each grid square and get a single point location if that's what you want, or for whatever polygon you might have, for example. Generally, these are going to be Cartesian, so they're going to use projections where we would expect those values to be in, for example, meters, so that's quite meaningful for us. And that's kind of contrasting with your kind of standard unprojected latitude, longitude coordinate reference system, which may be measured in degrees, right? So that's always kind of an issue. You want to measure in a meaningful spatial scale, so that's why we like meters. Measuring in degrees, doesn't really mean very much and isn't really something that you want to be working with, at least for doing the types of spatial analysis that we're doing. It will still work, but it's just that you can't really interpret easily the results that it's produced. Okay, so we've spoken about this already, about lines and points, and we can actually extract the direction for lines, and we will show that today. But very often we're going to be working with point data. So how do we calculate geostatistics? And there's lots of different ways. Obviously, there's the kind of very basic Excel, XPSS, standard kind of spreadsheet, standard statistical programs. Generally, I don't recommend this. Then they don't really allow you to visualize the data as you may want to do. You can carry out the calculations when you know how. So, we could write some of those statistical equations out manually within Excel, but ultimately it wouldn't really mean that much. So I do actually occasionally just do this just to make sure that, to remind myself how to do something, perhaps when I'm preparing for a course, just to remember how to do a particular function, but don't do this in reality. Either use a GIS platform for which you probably got access to ArcGIS, or as I used, a QGIS, so that's the open source version. Or you can use R. So as we're going to show later on within this session, you can do quite a bit of calculation within R, and that's actually becoming much more popular to use that statistical software in order to carry out spatial processing activities. Okay, so measures of spatial tendency. So the central feature is going to be the first type of processing that we carry out. Okay, so what we want to do here is, imagine we have a set of points, and we want to find the very central point within that data set. Okay, and that's useful for us in a number of different ways. So I'm going to give you an example of how we do this. But essentially what we're going to do is we're going to find the distance from each point within our data set to every other point. And then we're going to sum all of those points, all of the distances, and then we're going to find the single point which has the smallest distance to every other point, okay? So don't worry if you didn't understand that, we're going to work through that in a relatively easy way. And I'm going to be that crazy professor who talks about his dog. So here's a picture of George when we were walking in the evening sunshine in Cambridgeshire. To be fair, I have put a fairly heavy Instagram filter on this, but I do love showing this photo. And I figured it would just be a fun way to kind of bring him into this and give you a bit of an example of how we could actually generate spatial data from tracking, you know, in this case a dog, but you could actually apply it in field work if you wanted to track, I don't know, giraffes or some other sort of migrating animal, for example. So here we are, this is myself and George, and we are standing in the middle of a park, and George is basically running around and he's going to say hi to all of the other dog owners. And let's say that I've put the GPS monitoring device on him, okay? So you can create these, for example, you can just take a Raspberry Pi and you could have a cellular connection on it, and you could put it in a box and you could strap it to your animal, and you could just have it basically record a latitude, longitude location every 30 seconds using a GPS locator, and that would basically just give us a set of points which occur every 30 seconds along that GPS trajectory. Which means we basically just end up with a set of black points like this. So it's very easy for you to then to interpret. The question therefore is, well, which is the central point within all of these, okay? So how do we carry out that process? And what we basically need to do, as I already mentioned, was we need to get the distance matrix. So this is just a complicated way for saying we want to measure the distance between every point, and then we want to create it in a kind of so in a grid pattern, so you can see the distance to every single other one. And then basically you can sum each column within that distance matrix, and it'll give you the sum between that point and all the others. And then you can get the minimum out of all of those sums, and that would be the central feature, okay? So when I say we get the distance between each point, you can see here for this first point in the data set, we're going to measure that to every single other point, and then that would be one column in the matrix, and then we can do that for every other point, okay? So how do we measure distance? And this matters because we're going to be measuring distance in order for us to actually carry out this distance matrix. So the Euclidean distance is basically the Pythagorean distance, which is the straight line distance, okay? So it's as the bird flies. And what's nice about this is that essentially if we have 2 points, okay, in a map like this, so you can see here we have point xi and yi, and we have point xj and yj here. We want to get the distance between them, which is essentially the hypotenuse in a right angle triangle. Well, actually then, given the fact that we are able to calculate the distances a and b here, then we can use Pythagoras in order to basically calculate that straight line distance between the points, okay? So we know that we can use this version of Pythagoras here. So essentially what we're doing is we're saying, get me the x coordinate for the two different points, and we're going to subtract the second one from the first, so it's xi minus xj, and then we're going to square it, and I'm going to add it to the same but for the y coordinate, so it's yi minus yj squared, and that's going to give us the basis for the actual distance here, and we just take the square roots at the end so that we're back into the original units that we used, and that should be this Euclidean distance here between these 2 points. So thankfully this forms a right angle triangle, so it's a really easy way for us to calculate distance on a map, and this is kind of fundamental to so many of the spatial processing techniques that we're going to be using today, because distance is going to be a key part. There are other definitions of distance before we kind of get back to the central feature part, and I just want to take one slide basically to explain about that. So in the previous one we looked at basically the hypotenuse. So for example, in this map here we have the flight Chicago to Columbus, Ohio, which I took January 2020, so literally before COVID caused us all to, unfortunately, have our lives disrupted for a very long time. And imagine that rather than taking this direct flight here, like I did, imagine we took the Manhattan distance. So it's called the Manhattan distance because it basically is taking the distance at a right angle. So imagine it's a grid system. So obviously, if you're stood in Manhattan, with the exception of Broadway, you're always going to need to walk along the grid system, okay, to get anywhere. So you can't take the hypotenuse between your origin and your destination. You're going to have to go along a certain number of blocks and then across a certain number of blocks. So you're basically going to be taking this right angle distance here, okay? And that's why it's called the Manhattan distance. And in order to get that dij value, which is basically the distance here, between these 2 points, but in Manhattan distance, you would basically subtract the coordinates from each other and then you just add them. And what you're going to be getting is basically the distance for these two sides within the right angle triangle. And then that's going to give us the distance using that particular approach. Okay. Now we could take the network travel distance. All right. So every time that you don't know where you're going to go into your Google Maps and you're going to say, I would like to go to, let's say you're going to go to DC, and you're going to say, I want to go to DC. It's going to work out where you are now, and you're going to click directions and start, and what that's going to do is it's going to basically say this is the road network, this is the start and the end position. So we know the end's Washington DC. It's going to say what's your starting position. Your starting position is GMU campus, and then it's going to go through the whole road network to find the shortest path that it could take in order to get you there. Okay, so if you do it on this map here, the road network basically is going to take you this particular route, say down just north of Indianapolis, and then all the way up to Lake Michigan, and then finally into Chicago. Okay, and that's obviously going to be another different way to measure distance, this time arguably much more realistically, because it's actually along the travel distance that if you need to ship some cargo, it would need to follow that road path. Okay, so that's a bit of a tangent, but it's just important to recognize there are lots of different ways that we can measure distance. So going back to that central point example, and you've got this in the book, okay, so really what I'm doing here is just giving you a bit of a flavour for how we carry this out, hopefully in a more fun fashion than the kind of relatively dry textbook approach. So you can find the central points, and you've got this graphic within the book, and you can examine the distance matrix that's created from it. So what's the real world application? Well, imagine that you own a set of distribution warehouses. In fact, just imagine you're Amazon and you've got a set of distribution warehouses, and you need to work out where you want to put your hub for a new service or product that you're going to offer, and therefore you want to minimize the distance between that one and all the others, because you need to basically, maybe you need to do some sort of processing of that product and then spread it all out to all of the other warehouses so that then they can go on to consumers who order the product. Well, then you'd want to find somewhere that basically would provide you with the minimum distance to all other points within the network, and that's why this type of approach would be useful. Okay, because if you just took the mean distance between all of those points, you might be at a location that's not actually on one of the actual hubs that you have, and that's kind of what we're going to cover next, and that's why you kind of have these differences. This would give you specifically a single point in your data set that is the central point relative to all the others. So going on to the mean center then, this is the average location of all of the points in the data set. So think of it as the arithmetic mean center. It's the center of gravity for all of the points that you have. So it's quite easy, I think, for you to kind of understand, and also quite easy, hopefully, for you to calculate. And the way to do that is we get the sum of the Cartesian values basically as the numerator in the equation, and then we divide it by the sum of the total number of points as the denominator in the equation, and that provides us with you do this for the x and the y coordinates, so that provides us with then two mean coordinates which form this mean center place. Okay, so imagine that this is Ed again with George in the park, and there's all of these other exciting dogs, and he's running around going crazy, seeing all of the other dogs, and we create our GPS trajectory with our time-stamped locations, okay? And that gives us a set of points like this. So what's the mean center here, okay? So it's not going to be landing on existing points. It's highly unlikely to land on existing points, but it's probably going to be around this location here that I put theoretically this red point. So the key point is that it doesn't land on one of your existing locations, but it does represent overall the middle essentially. So how do we do that? Well, I mentioned already that we need to find the mean for the x-coordinate and the y-coordinate, okay? So you'll remember that the x bar here is representing the mean because it's got a bar on top of it. Same for the y bar over here, it's representing the mean of the y variable. And then just to find that, as I mentioned before, qualitatively, we need to sum all of the xi coordinates as the numerator and divide by the number of coordinates that we have, n, so the sample size, in order to get that mean value. And then we can do the same for the y as well, okay? And the book has an example within this table 4.3. And then essentially you would end up with a mean center like we have over here, okay? So I've provided you with a way to kind of think about this, and you've got the version in the book as well, just to follow up on page 63, 64, in case you need to just take a double check. But we'll be able to calculate this within the lab fairly easily. It's really not that much more advanced than what you've already done in the previous arithmetic mean calculations, okay? But just to mention, and this comes up a lot in my own work, that obviously doesn't necessarily mean that that mean center is going to be within, for example, an area or a set of polygons that you're analysing. And a good example is Maryland here. So the actual mean center will be skewed westward by that part of Maryland that stretches out over towards West Virginia. And essentially that's an issue because it does mean that you might do some calculations like I do quite regularly, and the point might not be within the polygon that you want. Okay, so let me give you a different example. I do a lot of fiber network planning for broadband networks, and often it might be that you write some code and it suggests a place for a new node that you need to locate, and unfortunately my code might just have put it in the middle of a lake, or it might have put it in the middle of an ocean. A good example is in Indonesia, where you have so many different islands. You're kind of planning which way the routing should go, and you might accidentally put something in the sea, and it's kind of down to this mean center approach. And that's kind of a limitation of this type of method, okay? So it's just something to be aware of. It basically means that you probably need to create a separate method if you want to avoid this happening, okay? So you can ex post rejig where those points are, but actually you're better off probably ex ante, so beforehand, actually working out a way that produces a sensible suggestion, but whereby it isn't actually in the center of a body of water, for example, or outside of some sort of polygon that you're working with. So when I refer to ex post there, what I mean is looking backwards, so after the event, or ex ante, which is before the event, essentially. Okay, so the geographic centre of the United States over time. So this just gives you an example of how the actual centre of the US population has shifted really quite significantly from 1790 through to 2010. So just to give you an example, 1790 over here, so you would have had your original 13 colonies around then, basically all aligned along the west coast, so the east coast. So a very short time after independence, and then slowly the population obviously moved westwards, and then over that time period the actual growth and expansion of the population and the spreading of the westwards of the main populace led to this centre basically moving both west and south simultaneously. And obviously after 1940 it started to move west and south quite at kind of a faster rate. You see here how it's kind of on the same line, and then after 1940 it starts to diverge quite a bit, and that's because around 1940 onwards, so when the United States entered the Second World War, a lot of those soldiers, and so soldiers, also naval seamen, were basically people taken from the industrial heartlands in the northeast, what's now kind of unfairly referred to as the Rust Belt area, and basically moved down to California. So for the Pacific Fleet, obviously, to go across, fight in the West. And as a consequence of that, a lot of sailors and people, when they came back from the war, realized that, well, California is quite a nice place to be. And actually, a lot of people ended up staying as a consequence to that. And then, the growth rates for Los Angeles and for San Diego and for San Francisco, post 1945, when the war ended, were really quite high. There was a huge population expansion, huge expansion in the West Coast in that area. Today, California being something like the 5th largest country in the world on economic size, if it was classed as its own country, right, aside from the United States. So absolutely colossal in terms of the actual size of the population and the number of companies it's producing. Okay, look, I digress a bit. Let's move on now to the weighted mean center. So before we were kind of focusing just on where the mean would be, but actually we did cover the weighted mean in the previous lecture. So that's maybe where you have a set of weights that you want to use to actually reflect the underlying size of some data points that you maybe have. Okay, so this could represent, the weight could represent the population or the income or the number of crimes or the cost or the magnitude of some sort of event which took place, in this case, in some sort of spatial context. Okay, so let's say that we go back to our warehouse problem again. You might be interested in actually trying to include the overall capacity of the warehouse or the floor space of the warehouse, so that you had some understanding of where you probably have the most capacity either available, or maybe you could do that with maybe where you think the most demand is going to be. That'd be a different way to do it, and that would kind of give you different measures, but they would tell you different things. Okay, so the first measure would be indicating kind of where you should probably locate if you want to take into account the existing capacity which you have, which may save you money. Or secondly, if you looked at that measure which relates to demand, so where people may buy your product, the weighted mean center may help you understand more about where it may be cheaper to kind of distribute to those buyers. Okay, so often, if you're making a decision to locate a company in a particular place, these are the types of metrics that could be produced very often by, they might get in an outside company who just does location analytics, essentially. I know that this was kind of a big thing maybe like 10, 15 years ago. New supermarkets or maybe new malls would decide kind of where they wanted to locate so that they were somewhat equidistant between existing competitors, and therefore they kind of had an actual market that they would have a clear competitive advantage with by locating in one specific area. So anyway, these are all things that you could take up as job opportunities once you spread your wings from GGS 300. So look, the way that you can calculate this, again, you're going to need to do it for the x coordinate and the y coordinate, and you're going to want to get the mean, but the difference is that you're going to take the sum of, and you're going to multiply the frequency, which is the weighting, by the coordinate, okay? And then you're going to want to take the sum of that as the numerator, and then you want to take the sum of the weights, so the frequencies, as the denominator, and divide the two, and that will give you the mean for the x in this case, or the mean for the y. So we can take the weighted mean center for the economic center of gravity for the world. So if we look here around about, a 1 AD, so this is basically kind of the, so this was a very long time ago. You're going to have quite homogeneous population spread between kind of east and west. So obviously, China had a large population then, Europe did as well, and this is relatively central in the overall spread of the kind of the world. But over time, essentially, what you basically had was, as Europe industrialized over the past 300 years, you had a big shift of the economic population to this area here. Post-war, this is the effect of the United States growing hugely. You see by the 1950s, all the way over here. And then eventually, as you had places like Japan as well starting to go through their kind of post-war reconstruction, and boom, eventually this center of economic weight started to move. And I think in the last 20 years, what you've basically had as well is the rise of China and other parts of East Asia, which traditionally over the last century were laggards in economic development, now starting to dominate many industrial production processes. So this is how things have changed over the last 2025 years. Okay. Median center. So this is a location that minimizes the sum of the unsquared distances. Now it's not an easy metric for us to kind of calculate explicitly, okay? So we're going to calculate it using a repetitive process. So basically to get this metric, this is the position which would have the minimum travel distance to every other point, so the Euclidean mean. But because it's computationally difficult, we basically take an iterative approach, and we basically take the minimum distance to all of those, to every point, okay, in order to get the median. So this is how we calculate it. It's somewhat more complicated than the others because we don't just get a single metric, but it's important for me to actually indicate that this is what we would get. You'll find this relatively familiar in here because it's similar to the other measurement distances kind of formulae that we already looked at. The only difference is that we're minimizing the results that we essentially get, okay? And that's how we get this, this set of median center coordinates here. So the median center is somewhat differently defined by the Census Bureau. So in the census in the US, it uses the median center as the place where half of the population is north versus south, and half of the population is east versus west. Okay, so you can see here for around 1880, it was somewhere in northwest Ohio, and then eventually it started to move quite significantly down to the southeast. Or it's moved southeastwards through Indiana over time as the population basically has hugely expanded in the southwestern area of the United States. So the linear directional means, you'll remember before that I spoke explicitly about the fact that we're going to be using mainly points, but we can use polygons as well, and we can convert them to points, for example, or we could use lines, and those line strings could actually indicate a specific direction. And if we had a lot of those specific directions, then we'd be able to create an average line, which kind of takes into account all of the existing directions that we have, and then would find the mean across them. Okay, so the resulting value for the linear directional mean shows the angle of the mean vector, and we can basically take this set of what looks like arrows here, but just imagine them as lines, and we could get a mean for all of these. Okay, so this could be hurricane trajectories, or this could be directions for Earth's geomagnetic field at a 1 kilometer level, and then basically we can get an overall value like this. So we can calculate that by taking the arctan of this equation here. So it's the sum of all data points for the sine and theta I as the numerator, and then you've got the same down here for the cosine theta I. And basically you can run through this, and it's fairly straightforward. We're going to go through this in the lab, and it just produces you with this kind of directional mean. Okay, so here theta I is the key input representing the direction of the set of the linear features. I think I mentioned before that usually before I moved to GMU, I'd always be in DC for September time because there was a conference that I would go to there, and every year that's the back end of hurricane season. So I'd be watching on the news, and often we would end up getting the kind of the back end. Thankfully, once they'd made landfall and kind of pushed up the eastern coast, so it would be very much kind of more subdued than the real hurricane, but it would still rain a lot and be pretty stormy weather by the time it got up to kind of Northern Virginia area. But I would watch on the Weather Channel and the news, and basically you would end up with all these hurricane tracks, and these hurricane tracks essentially would basically represent potential projections. So here I think these are the actual hurricane tracks that have taken, but you could also simulate future hurricane tracks and take the linear directional mean for them in order to try and give some sort of direction as to where they might go. But I mean, this is historical data, so this is just basically saying this is where they pretty much standardly go, and obviously they kind of make landfall somewhere around the Caribbean here, push at the coast, and then they might make landfall again when they hit the United States up here, particularly Florida and Georgia, for example. Okay, so let's move on from that then and now talk a little bit about spatial measures of dispersion. So these are cool statistics because they're kind of nicer than the kind of one single metrics that we might produce previously for kind of just parts of, for kind of representing in a single figure the kind of the central tendency for the data. Here we get a greater understanding of the kind of the spread of the distances across a distribution of data. So for example, with the standard distance, this is going to be very similar to the standard deviation. So this basically measures how much absolute dispersion exists in a point data set. So when I say absolute, that means just think of it as that the actual metric which you're getting stays in the original units of the data which you analyze. So let's just imagine that these are distances in meters. That would mean that the standard distance that we would get would remain in meters, okay? So we do take the sum of the squared differences here, but then we take the square root at the end to convert back into the original figures, okay? So the absolute dispersion, so the standard deviation, for example, is dependent upon values for the mean. There's two equivalent formulae. So we can take this one here. It looks very similar to what you calculated already for the standard deviation in the previous spatial statistics class. The only difference here is that we're using x and y coordinates, so we do it for each of them. And basically this produces a number in meters, which is basically the standard distance for that data set. So just to give you an example again, let's go back to the set of points that we generated from within the park. You can see that there's a different degree of dispersion between these two data sets, okay? So in the first one here, we've got quite a large spread across the data points, and it's because George is running off to see all of these other dogs, okay? And it leaves us with this quite a large amount of variation. Maybe I went to a park on another day and there were no dogs around. Maybe he would stay a lot closer to me, so there'd be a smaller amount of dispersion among those coordinate points that we ended up producing from his GPS tracks from his collar. Okay. So we can also take a weighted standard distance. So this is a little bit like the weighted mean that we took before, but this time we're going to be weighting it based on some sort of frequency data which we have. Okay, so it's the same idea as the weighted mean, and f again is the weight variable. Okay, so we just have this different way of calculating, and I'm going to use this bottom one down here because it looks more similar to the ones that we've used before. But basically you're taking the sum of the squared differences and basically then you're multiplying them by the frequency, so the weight that you have, and you're doing that for the x and the y coordinate, and then you're dividing by the frequency weights, the sum of the frequency weights for the data that you've got. And this provides us with our weighted standard distance, so SWD. Okay, so imagine again this kind of warehouse example that I keep going back to, which essentially is indicative of us maybe having different floor spaces at different warehouses, and that's kind of important because you might have one warehouse that's really close to where you want to be, but you've got no floor space there, and that's going to really affect your ability to actually operate from there. So maybe you want a measure which takes into account the amount of available floor space that you might have. Okay. So moving on, we do also have something called the standard deviational ellipse, and this takes the kind of orientation of the points that you may have into account with the standard distance. Okay, so the calculation procedure for this is to calculate the standard distance separately for the x and y coordinates, and then basically to create a cross of dispersion by drawing the lines for the SDX and the SDY from the mean center parallel to the different axes that you create. So don't worry if this doesn't mean anything to you yet. We will go over this and you'll be able to understand exactly what this means. So then we can cross-rotate this axis that we create using a trigonometric function to minimize the distance of points across the arms, okay? And this is the way that we do this for the SDX, so the x coordinates here and the y coordinates here. And you'll see we're subtracting the mean from each of the coordinates here to get the sum of the squared differences, dividing by the total number of samples that we've got and taking the square root to get the standard distance first. And then once we've got that, we can create this ellipse. Okay, so we've got the mean center down here. We're able to create this cross of dispersion using the standard distance for the x and the y coordinates. Okay, so we take the SDX and the XDY and we create this ellipse that we're interested in, and then we can rotate it. Okay, so the outliers do affect this ellipse quite strongly. And the study area boundaries might be a contributing factor to the overall shape. So if that's all very theoretical for you, don't worry, because in the book we have a nice example, and they're looking at the different number of piracy interactions in East Africa. Okay, so take Somalia for example. There's really not very much economic development, there's a lot of deprivation, and Somalia actually has home to a very large number of pirates, modern day pirates. So they have really quite advanced technology, and unfortunately what they do, because there's not much else to do for a livelihood in Somalia, is they go out and they try to interact with shipping that goes up this east coast of Africa, okay, and basically they try to rob the boats or to take things from the boats or to take the boat altogether. And what's happening here is they're comparing the number of interactions between 2009 and 2010, okay? So you can get some understanding of the anti-shipping activity across the African coast for 2009 and 2010. And really what's kind of happened is that between 2009 and 2010 is the boats that they were using advanced a lot. So basically maybe the pirates were making a bit of money and they went out and they bought new boats, faster motorboats basically, so they're speedboats, huge engine on the back, and they can go much faster and much further, so that they're even trying to interact and board boats all the way out here off the African coast. It's really crazy. So this is where you've had anti-shipping events. So maybe that's someone trying to actually take on board the boat, or it might also be a point where you have an intervention by a military vessel also to try and prevent this type of activity. But the point is that we can use these different ellipses to see the area that these boats are operating in over these two different periods, and you can see that by 2010 it's expanded the radius to a much greater degree. So the spatial issue of relative dispersion. So I said before about absolute dispersion, which is in the original units. Remember, in relative dispersion, what we're talking about here is a relative to all the other points. So think that percentages are a relative measure, okay? So they're not in the original units, they're indicative of a value between two set points, in our case for percentages between 0 and 100. And we can use this similar kind of notion, albeit in a different way. And there's some limitations to this, and that's why I just want to bring them up and discuss them here. So in descriptive statistics, we have the standard deviation, which is absolute, because the standard deviation gives you the average movement around the mean in the original units. And then we have the coefficient of variation, which is essentially relative. So remember, it could be a value between 0 and 1, which is the true coefficient, or you could think of this as a percentage. So maybe you can multiply it by 100 and it would say whether it's 25% or 50% dispersion. Okay, so you compare different data sets in different units. In geostatistics, there's no exact spatial equivalent to the coefficient of variation. Okay, so when the coordinate systems change, the mean center changes, but the standard distance does not. So let's go to our example over here. This is one coordinate reference system. We've got a mean center of 3.81, 2.51. You can see the location of B, C, G, D, F, A, and E. The difference is that then when we convert them to a new coordinate reference system, we end up shifting all of these points, and you can see now the mean centre is 6.8 and 3.51. But the actual distance between the points hasn't changed at all. So the dispersion measure hasn't changed one bit. It's just that now you're projecting them in a different form, and therefore you've got different coordinate reference points. Okay. So actually understanding the standard distance or the mean centre ratio in this case is not that useful. But we do know similar point patterns in different areas should have different levels of dispersion. So we can basically say, all right, we want to analyse these points here, but we want to have some sort of additional boundary that maybe we want to introduce. So that means we need to kind of approach this in a particular way. So I've taken these examples from the book. We've got case 1 on the right here. And here what we have is the same absolute dispersion between these 5 points. So if you look in the small box, the distance between these points is the same as the second box, and actually it's the same as in the third. The only difference is that each time the kind of polygon, circular boundary, oval boundary almost, around the outside has got larger, and that means that the dispersion between the points, the absolute dispersion stays the same, but the relative dispersion between region A here and region B and C here is basically decreasing. Okay, and in the second group, what we have is we basically have these points here within this much larger box, and we have a second set of points here, and essentially what we have is very similar dispersions, so that these points relative to the outer box don't change much between these two, but there will obviously be very different standard distances between these two different types. So we kind of want to account for these, absolute and relative point patterns. So what's the solution? Let's see the next slide. So we can take the relative distance. So the relative distance is a measure of the relative spatial dispersion based on a point pattern, standard distance, and the size of the study region. Okay. So what we're essentially doing is we're starting to introduce a denominator which kind of controls for that area that we're interested in. And that could be, you could use the radius of a circle with the same area as the study region. So you can see here we've introduced these kind of polygon, shapes around the outside of the points. And actually, if you know the area for each of those polygons, which we can do fairly easily because, in ArcMap or in QGIS, you can find the area of the geometry area of that item really quite easily, just with a couple of clicks. And then once you've got it, you can solve the radius for a circle just by using your standard area equals pi r squared approach. So if we were able to do that, so let's say DC is 68.3 square miles, that's the area. We can use our pi r squared equation to calculate that the radius is 4.7 miles. And then this allows us to basically start providing the standard distance here as the numerator and the area radius as the denominator here in order to get our relative spatial dispersion measure here, RD. Okay, so this allows us to compare point patterns in differently sized regions. Great, well, I hope you enjoyed the lecture. Obviously, this has been relatively high level and theoretical, and you've got the book to read along with this, so let me just check. That's chapter 4. You'll recognise quite a few of the actual graphics that I used within the lecture today, so hopefully it's fairly easy for you to read along and understand the content that's there. In the lab, which we're going to go to next, I will run over some of those calculations within R, and then I think there'll also be just a little video which will show you how to do some of these spatial computations in ArcMap as well, so you might need access to that. So thanks for tuning in, ladies and gentlemen. It's been great to see you, and don't hesitate to reach out to me if you've got any further questions about any of the content. So thank you very much. Have a good day. I'll see you soon. Goodbye.